Okay, so up until now, we've been assuming that the force that is being applied to do the work is constant, and it stays constant throughout the displacement of the object. Okay, but that is not necessarily true in all cases, as is the case of a rubber band. So I'll just show you what I mean. So till now, whenever we used to calculate the work done, we used to take, so like even in the case of dot product, we used to consider two vectors, and we assume that this vector, the force vector, if this is the force vector and this is the displacement vector, we assume that as the object moves along the displacement vector, the force vector stays constant and its magnitude does not change. Okay, but if we see the case of a rubber band, okay, that is not true. So the rubber band is similar to the case of a spring, and okay, so here you can see, as I start stretching the rubber band, when I have to stretch it for the first 1 centimeter, I don't need to actually apply a lot of force. So it takes quite a bit. It just takes a small amount of force for me to stretch it for the first 1 centimeter. But after that, for the next 1 centimeter, I need to apply a bit more force, and then a bit more force. And as I stretch this, I need to keep on increasing the force that is being applied by me. So the force clearly does not stay constant throughout the whole process, and as I stretch it, I need to keep on increasing the force being applied. Okay, and if I plot the force that I'm applying versus the displacement of the lower part of the so versus the displacement of this part of the rubber band, so it displaces from this point to this point, right? So as it moves along this path, if I plot the force, I what I get is actually a straight line. So why would I get a straight line? Well, as I just said, this rubber band is similar. The rubber band is similar to a spring, right? And in a spring, you might have studied earlier the force that is being applied by a spring. Okay, so that just broke. Yeah. So the force being applied by so yeah, even this is even better, right? So the force that is being applied, the restoring force that is being applied by the spring or the rubber band in this case, is all obviously equal to the force that I am applying, right? And that force is equal to, so that is equal to minus, so that is the minus was there for the restoring force. Okay, but here I am applying I'm applying a force in the downward direction along the direction of displacement, so I don't need a negative sign there. And then we had the spring constant, which in this case represents the elasticity of the rubber band, and then we have x, which in this case is simply d. So I can actually write an x there. X means the amount of rubber band that has been stretched, the length of the stretched rubber band. So I can write an x there. So the force that I am applying is proportional to the amount of or the length of the rubber band that has been stretched. Okay, to the extent of which it has been stretched. So if I plot this, so here clearly this shows that F equals kx. Obviously we should get a straight line, right? With okay, and if we plot it, we get a straight line, and the slope of this line is k. Okay, that is very obvious because this is so yeah, this is obviously the equation of a straight line, y equals mx, if you want to write it in general form, where m is the slope, and so here is k is the slope. So k is the slope, and we are plotting f versus x. Now how do I find the work that has been done by me on the spring, on this rubber band? So I've done some work while stretching it, right, for it to gain some potential energy. Okay, so how do I find that work? So let's say I start at this point. Okay, so I'm at this point and I move from here to here. I take a small step. I displace it just a bit. So earlier I was at this point. Okay, so I had stretched it this much. Okay, so this distance actually represents this much. Okay, this much amount of this length. Okay, and then I take it I stretch it just a bit more. So I stretch it just a bit more, and in that one step I increase the force. The force increases from, okay, so it goes from this point to this point. So this is just a small change in force. And if I assume that the force is constant during that small step, I can actually keep it. Okay, so if I assume that it remains constant over that small period of time, I can actually find the work done in that small step. So in that small step, when I move from here to here, okay, if I assume the force is constant, I can find the work done, and that work done will be this much force. So force work done is force times displacement, and the displacement is this much, right? So this much times the force applied. So what I get is this into this is the work, and in which diagrammatically is being represented by this area, okay? Because the area of this rectangle also this times this. So the area, this small area, is actually the work done when it stretch the rubber band from this position to this position. And similarly, I can find the work done when I stretch it from this position to this position also, which is which is represented by. So that work is represented by this rectangle here. Actually, this rectangle here. Okay, so this area represents the work done when I take it from here to here. And similarly, I can do it for all other points by taking small steps. And what I end up is, so let's say this is the point till which I stretch the rubber band, this point. So this whole area, so if I add up all those rectangles, okay, small steps, I get this whole area. So this whole area represents the work done by me on the rubber band when I take it from 0, so point 0 when the rubber is not stretched, to this point when the rubber is completely stretched. So this is my rubber, let's say this is my rubber band, okay? So when this is without elongation, and when I elongate, let's say it stretches to this position, okay? It gets this long. So this is x, okay? So this is what I'm plotting here. So as I stretch the rubber band from this point to this point, this area represents the work that I have done. And we all know, when you have to find the area under any curve between two limits, we actually use integration. So here we can simply, so where the force was constant, we used to simply multiply the force with the displacement caused. But if we don't have a constant force, what we can simply do is we can simply integrate and find the area under the curve. So what we can do is, and okay, so so we can write this as an integral, okay? So first of all, what is the area of a single rectangle here? The force at any point, let's say the force at this point, which is F, times a small change in the position of the rubber band, okay, which is dx. So x is being represented here, right? A small step that I have taken while stretching it. So that is the area of the small rectangle, and then I have to integrate the area of all those rectangles, all the small rectangles. So I write an integral sign there, and therefore the total work done from this position to this position while I stretch the rubber band in the whole process is given by an integral of f dot dx. Now okay, so that is how we can find this, and in the next video we'll see how do we actually calculate this integral, okay? So yeah, that's it in this video. Bye.